Starship's decade-long quest conquers cosmic challenges. Hot staging, Mechazilla, and Raptor engines push limits. Can SpaceX redefine space travel? Join Starship mission updates. Let's unravel the rocket's toughest hurdles. It has been over 10 years since the Starship project began development. While SpaceX has achieved some impressive milestones, the vehicle is still likely years away from becoming fully operational. So why is Starship so difficult to get right? Elon Musk once said that Starship absorbs more of his mental energy than probably any other single thing. It is so preposterously difficult that there are times when he wonders whether SpaceX can actually do this. Musk later broke down why building this massive two-stage rocket is such a monumental challenge. He said Earth is a tough place to launch from. We've got strong gravity, the strongest of any planet in the solar system, and a thick atmosphere. That combination makes getting to space anything but easy. A typical orbital rocket, he explained, might be able to get about 2% of its liftoff mass into orbit. Then he added, "To my knowledge, no rocket has ever lifted about 4% of its mass to orbit, and to make a rocket fully reusable, that's pretty much what you need, 4% or more. That's never been done." What Musk is talking about can actually be explained by the classic rocket equation. A rocket moves by throwing mass exhaust out the back at high speed, using the principle of momentum conservation. But here's the catch. A rocket needs fuel to carry both itself and more fuel. And to carry that extra fuel, you need even more fuel. It's a tricky compounding problem. That's why just getting into orbit is already incredibly hard. Now imagine trying to do that and making the rocket come back down safely so it can be reused. That adds another level of complexity. You don't just need extra fuel for the return trip. You also have to deal with re-entry for Starship's upper stage. That means carrying a heat shield and aerodynamic flaps, which add even more mass. So how can SpaceX actually pull this off? Well, first they use every technique and trick available to squeeze as much performance as possible out of the rockets. One standout example is the thing called hot staging. At launch, gravity naturally keeps the liquid propellant settled at the bottom of the rocket's tanks. So when the valves open, gravity helps the fuel flow smoothly into the turbopumps. This works just fine for the first stage because the engines are firing and generating strong upward acceleration, which keeps everything in place. But things get trickier with the upper stage. Once the first stage booster shuts down, the rocket stack is essentially in freefall. Without that acceleration, the propellants in the upper stage begin to float around inside the tank. That creates a problem. When it's time to start the upper stage engines, there's a risk the turbopumps could suck in helium gas or a frothy mix of helium bubbles and liquid fuel, instead of a steady stream of liquid. If a pump designed to move liquids suddenly takes in gas, it can overspeed. In a rocket engine, that kind of failure can destroy the system within seconds. This was a major reliability issue with early launch vehicles. To solve this, older rockets used small solid fuel rockets called ullage motors. These were fired just before igniting the upper stage engines to push the fuel back to the bottom of the tanks and to help separate the stages cleanly. Hot staging provides a simpler and more efficient solution. Instead of shutting everything down and using ullage motors, the upper stage engines are ignited before the stages separate. For Starship, this means the super heavy booster shuts down all but its 3 center engines, while the second stage lights its engines and effectively pushes itself away from the booster. There are several advantages to this method. Hot staging eliminates the need for complex sequencing or extra hardware, like ullage motors. It also keeps the rocket accelerating almost the entire time, which is critical because of the rocket equation mentioned earlier. Saving even a small amount of fuel early in the flight can significantly boost efficiency. The faster the rocket reaches orbit, the less fuel is lost to gravity. Elon Musk has said that using hot staging on Starship could increase its payload capacity to low Earth orbit by up to 10%. That's a substantial improvement from a single design change. Falcon 9 doesn't need to use hot staging because it's already a relatively lightweight rocket that can carry a good amount of fuel. Plus, most of its payloads are usually on the lighter side. so it doesn't face the same challenges as Starship. Another way SpaceX aims to boost Starship's performance is through a system called Mechazilla. This launch tower is made up of steel truss sections and features a pair of mechanical arms. Before launch, these chopstick arms stack the super heavy booster onto the launch mount and then place the Starship upper stage atop the booster. Just prior to liftoff, the tower's ship quick disconnect arm supplies fuel and electrical connections to the Starship upper stage. After launch, the tower shifts from assembly to recovery operations. The same arms that help stack the rocket now capture the returning super heavy booster and eventually the Starship itself. Elon Musk has stated that Mechazilla's landing method significantly reduces turnaround time between launches, allowing for faster reuse, which is a major advantage. Additionally, this approach reduces the rocket's mass and mechanical complexity by eliminating the need for landing legs. Because Starship is much larger and taller than the Falcon 9, using landing legs would require them to be bigger and heavier and possibly increase from the Falcon 9's 4 legs to 6, adding more weight and complexity. Mechazilla's arms allow for a more streamlined design and efficient recovery. Hot staging and Mechazilla kits are impressive ways to make Starship more efficient, but the true enabler behind the massive scale of this vehicle is the Raptor engine. Raptor runs on subcooled liquid methane and subcooled liquid oxygen, operating in a full-flow stage combustion cycle, or FFSC. This cycle is a twin-shaft stage combustion design that uses both oxidizer-rich and fuel-rich preburners. The FFSC design allows the full flow of both propellants through the turbines, avoiding the loss of unburnt fuel or oxidizer. One of the key advantages of this approach is that the energy generated by the preburners, which drive the propellant pumps, is distributed throughout the entire fuel flow. This means the exhaust gases powering the turbines are relatively cool, even compared to other closed-cycle engines that only preburn one propellant. As a result, the engine experiences lower thermal stress and enjoys a longer operational life. In contrast, open-cycle engines divert preburner exhaust away from the main combustion chamber and must minimize the amount of propellant fed through the preburner. This is typically achieved by running the turbine at its maximum survivable temperature, which limits engine life and efficiency. Despite its advantages, the Raptor engine is extremely complex and difficult to engineer. Ignition is achieved through torch igniters located within each preburner. If a preburner fails to ignite or does not fire at the exact right moment, it presents a significant challenge. Unlike the Merlin engine, which uses a single shaft to drive both the oxygen and fuel pumps so that they always spin at the same speed, the Raptor uses separate oxygen and fuel power heads, each with its own turbine and preburner. These components must cross-feed and synchronize perfectly. This is why Elon Musk often describes the Raptor's ignition sequence as an elegant dance. The coordination required is extremely precise. Even a slight mismatch between the oxygen and fuel systems can lead to a stoichiometric mixture forming in the preburners. This condition is dangerous as it can melt or even detonate critical components of the engine. Because of this complexity, refining and stress testing the engine's startup and restart scenarios is crucial, especially in cases where one or more engines may fail to respond as expected. Another major challenge in rocket engine design is the nozzle. The nozzle is shaped to ensure that the pressure of the exhaust gases matches the surrounding air pressure as the gases exit. If the exhaust pressure is higher than the ambient air pressure, the gas spills over the edges of the nozzle, reducing thrust. While this doesn't damage the engine, it does decrease its efficiency. As a rocket climbs through the atmosphere, the surrounding air pressure drops. This means that no matter how carefully the nozzle is shaped, it will gradually lose efficiency with altitude. If the nozzle is optimized for sea level conditions, the exhaust will begin spilling over as the thinner atmosphere provides less resistance. However, since Starship's second stage only activates after the vehicle has passed through the densest parts of the atmosphere, its main engines can be optimized specifically for operation in the vacuum of space. To perform efficiently in space, the Raptor vacuum engine uses a much larger nozzle. In vacuum conditions, exhaust gases expand far more than they would at sea level, since there is no atmospheric pressure to contain the plume. The larger nozzle allows the engine to take full advantage of this expansion. The complication comes during ground testing. At sea level, testing a vacuum-optimized engine becomes risky, although it is acceptable for the exhaust to exit at a pressure higher than ambient. Serious problems arise if the exhaust pressure is much lower than the surrounding air. In such cases, air can force its way into the nozzle from the outside, causing the exhaust flow to detach from the nozzle walls. This leads to intense turbulence and rapid vibrations within the nozzle. If the pressure mismatch is too extreme, these vibrations can become so violent that the nozzle tears itself apart. To test the vacuum version of the Merlin engine, for example, SpaceX removes the nozzle entirely during sea-level tests to prevent this destructive effect. In contrast, the Raptor vacuum engine is built with a much stronger nozzle and is capable of operating at much higher chamber pressures. This higher pressure means that the exhaust remains strong enough to resist intrusion by ambient air, preventing flow separation. This capability is a significant advantage. It allows SpaceX to test the full performance of the Raptor vacuum engine on the ground, pushing it to its operational limits without relying entirely on computer models or waiting for flight data. Currently, Starship is still in its development phase and remains far from the performance levels Elon Musk has promised. However, there is reason for optimism. Both the engines and the vehicle itself offer significant room for improvement, and SpaceX is actively working to enhance them. One of the most promising developments is the Raptor 3 engine, which marks a substantial upgrade over its predecessors, Raptor 1 and Raptor 2. This sea-level variant of Raptor 3 produces 280 tons of thrust, a 51% increase compared to Raptor 1's 185 tons, and a 21% increase over Raptor 2's 230 tons. It is also lighter, weighing only 1,525 kilograms compared to Raptor 1's 2,080 kilograms and Raptor 2's 1,630 kilograms. Additionally, it boasts a specific impulse of 350 seconds, offering improved efficiency. These performance gains are the result of several major design innovations. SpaceX has eliminated or integrated many components directly into the engine. Numerous bolted joints from earlier versions have been replaced with single-piece structures, simplifying manufacturing. However, this change can make servicing more difficult, as some components are now located beneath welded sections. Beyond engine improvements, the final Starship Block 3 design is expected to receive a significant Delta-V boost. This will be achieved by increasing the number of engines, adding 3 more engines to the upper stage and 2 additional engines to the Super Heavy booster. These changes will contribute to greater thrust, improve performance, and bring Starship closer to meeting its ambitious goals. It's true that Starship is the most ambitious and challenging project SpaceX has ever undertaken. But if they succeed, it will stand as their greatest achievement. This is your mission update team with Starship mission updates. Starship's bold engineering redefines rocketry's limits. Like, subscribe, and keep looking up. Can SpaceX master the stars? Share your predictions below.